So this is for Calculus 2. We want to talk about trig integrals. And so let's recall some things first. So let's recall the following. So first, let's recall the Pythagorean identities. And so for the first one, we have the classic sine squared of theta plus cosine squared of theta equals 1 for all theta. And so what does this mean? It means, well, as long as these angles are the same, then this quantity is always 1. And why don't we take a brief moment and just see why that's true? That's not obvious at all. And also through that, we'll see why it's called a Pythagorean identity. So maybe on the side, I'll say why, right? Why on earth is that true? Well, let's say we have a right triangle. So here's theta, our angle. Here's A, B, and C. And so, yeah, let's just go ahead and take the sine of theta. So sine of theta, of course, is A over C. And let's go ahead and take the cosine of theta. That's B over C. And then to show that this is true, let's work with the left side of the equation and show it's equal to the right side. So we have, sine squared of theta plus cosine squared of theta by substitution, right? We know exactly what sine of theta is. It's this. So this should be equal to, what do you say? A over C, because that's sine of theta squared, plus B over C, that's cosine of theta, then squared. And we know how to square a fraction, so that's A squared over C squared, plus B squared over C squared. But that gives us common denominators. And since triangle ABC is a right triangle, by the Pythagorean theorem, A squared plus B squared must be C squared, since both A and B are the legs of the right triangle. But of course, any number over itself is 1. So yeah, that is true. And now you can see why it's called a Pythagorean identity. Notice again, the Pythagorean theorem pops up in the middle. Well, we could be kind of clever. So here's one important identity we'll need. And we have a couple more that we can find. So let's take this and let's do a little work. Let's maybe multiply the whole thing by 1 over cosine squared of theta. It's also known as secant squared of theta. And then, yeah, just go ahead and multiply through. Okay, so that's going to give me sine squared of theta over cosine squared of theta plus cosine squared of theta over itself equals 1 over cosine squared of theta. But we know that sine squared of theta over cosine squared of theta is exactly tangent squared of theta. Well, cosine over itself, that's going to give me 1. And then 1 over cosine squared is exactly secant squared of theta. So that's going to give me another identity. I could actually take this method, and instead of multiplying by 1 over cosine squared, I could multiply by 1 over sine squared, and that would give me yet another identity. But for this lecture, we'll just need this and this. Now, keep in mind, we have some algebraic flexibility with both of these. So, for example, this is kind of a buy one, get two free deal here. So check this out. So I could solve algebraically for sine squared of theta, and that's 1 minus cosine squared of theta. So for certain problems, it'll be handy to turn sine squared stuff into 1 minus cosine squared of theta stuff. I could also take this equation and solve algebraically for cosine squared of theta. And that would be 1 minus sine squared of theta. So now you can see what I mean by buy one, get two free. And we could do the same here, right? So we could take our second Pythagorean identity. And solve algebraically for tangent squared. So tangent squared of theta, that's exactly secant squared of theta minus 1. So you want to be careful here because the order does matter. And so we have it in this order. We could also solve algebraically for 1, right? So 1 must be equal to secant squared of theta minus tangent squared of theta. So we get another buy one, get two free. Okay, so we'll need those. We'll also need the power reducing formulas. These come from the double angle formulas for cosine. And so we get the cosine squared of theta is exactly 1 plus the cosine of a double angle over 2. And, well, not cosine. We already have cosine, right? So we don't want that twice. How about sine squared of theta? That should be the conjugate of this. So that's 1 minus cosine of 2 theta over 2. And you can kind of verify here. So you could take the sum of the left sides. That would give me cosine squared of theta plus sine squared of theta. And if this is correct, the sum should be 1. And in fact, the sum of these is indeed 1. So we'll need these. Okay, so let's dig in. Let's try some examples. Okay, let's start off simply, then we'll build up a little bit. So let's say we have the following. We want the integral of, let's try maybe sine of 3x. Let's do sine, how about to the 5th? And then cosine, how about squared of 3x dx? Now here, for integrals that involve products of sine and cosine, remember one thing we might try is to go to the factor that has an odd exponent and knock it down by 1. So let's see what we mean by this. So I'm going to rewrite this as sine to the 4th. So I knock the power down by 1. So sine to the 4th of 3x times cosine squared of 3x. But I can't just write that to the 4th, right? It would change that quantity. So algebraically, I need a factor of sine of 3x. That should make sense because the product of these two gives me this back. Well, the reason why this is useful is sort of the factor that you took out here. This should look close to a du in a substitution. So if my derivative is going to involve a sine, then my original function should involve a cosine, right? Because the derivative of cosine is negative sine. So yeah, if my derivative involves a sine, then my original function u should involve a cosine. So that means that we need all of this in terms of cosines. Well, we can do that. So remember, we just said that sine squared of theta is equal to 1 minus cosine squared of theta. Right? So that's true for all theta. Well, if we're clever about this, we can actually think about this in the following way. So this right here is sine squared of 3x squared. That's helpful. So that's helpful because I can replace this quantity with something that looks like this. Okay. Now this is already cosine, so we can sort of leave that alone. Okay, so remember, how do I turn this into cosine stuff? Well, by the Pythagorean identity. So we're going to abbreviate it. So my little justification over the equal sign. So by the Pythagorean identity, this is the following. So this is 1 minus the cosine squared of 3x, quantity squared, times cosine squared of 3x, times sine of 3x dx. Well, that's really nice because that sets us up for a u substitution. So we're going to let u equal cosine of 3x. We're going to take the derivative carefully using the chain rule. So that will be minus sine of 3x times 3. So the chain rule says multiply by the derivative of the inside. Now, this is what we're hoping to get rid of. So maybe we'll divide out the minus 3. And so we get the following. So that seems really good. I could have done some algebra here, right? I could have squared out this binomial, but I want to wait for the substitution because I think maybe the terms will look a little bit nicer. You certainly could if you wanted to. So if you wanted to square that out now, feel free. But again, I'm going to wait a little bit. So by our substitution, this quantity right here is replaced by this. So this gets replaced by minus 1/3 du. So that's this. Now here I've got 1 minus, so this is u, right? So 1 minus u squared, quantity squared, times u squared. And so we want to be smart about our algebra, right? So we want to follow, of course, order of operations. So let's square out the binomial first and then distribute the u squared. So let's just recall, I use this all the time. So a plus b quantity squared, that's exactly a squared plus 2ab plus b squared. Okay, so with that said, we should get the following if we're careful. Okay, so a squared, that should be 1. So plus 2ab, so that's going to be minus 2u squared, plus u to the 4th. So just following this here. And then that's times u squared du. And so, of course, I want to use the distributive property next. So by the distributive property, we have the following. So this is u squared minus 2u to the 4th plus u to the 6th. Remember to add those exponents when you multiply the same base, du. So this seems promising so far because now we can just use the power rule. So of course we want to recall the following. So if n is not equal to minus 1, then the antiderivative of x to the n dx is exactly x to the n plus 1 over n plus 1 plus c. Okay, so what do we have here? We got my minus 1/3. So this will be u cubed over 3. This is minus u to the 5th over 5, plus u to the 7th over 7. That seems good. Plus c, don't forget your plus c, right? Never forget. And then we want to do a back substitution because we started with variable x. We want to end with variable x. Okay, so let's go ahead and plug in. So let's just recall quickly. We said this was u, right? So I'm just, everywhere I see u, I'm going to back substitute. I'm going to plug this in for u. So cosine of 3x. So here, cosine of 3x, quantity cubed, over 3. Here. So I've got cosine of 3x, quantity to the 5th, over 5. And then lastly here, I've got plus cosine of 3x to the 7th, over 7. And that is plus c. So there we go. We've got the antiderivative of this integrand right here. Okay, so let's try one where we have purely even powers. So again, sort of the defining feature here is that we had a factor that had an odd power. And again, just to recap, our maneuver was to knock it down by 1. And the reason why we did that is you could see that set us up for a u sub as long as we involve that Pythagorean identity. So let's try this. So we want the antiderivative of cosine to the 4th of x dx. In this case, you're going to notice purely even powers, right? If a term has a purely even power and it involves sine or cosine, that's your big clue that you want to use the power reducing formula. So I'm just going to say recall that cosine squared of theta is exactly 1 plus the cosine of a double angle over 2. So that's quite good because we can write this as cosine squared of x squared, right? That is cosine to the 4th of x dx. And then we can make a substitution. Just instead of having thetas, we're going to have x. So we make that substitution. That gives us the following. And we know how to square a fraction, right? To square a fraction means you square both the top and the bottom. And of course, we want to recall our favorite, how to square a binomial. So that's a squared plus 2ab plus b squared. Now the denominator here, that's going to be a 4 in the denominator after I square that. I'm going to factor that out. So that's going to give me a 1/4 after I square this in front. And now I'm going to square this carefully using this. So that's going to give me 1 plus 2 cosine of 2x plus cosine squared of 2x. But what do we notice? We have a term with a purely even power right here. That means we have to use another power reducing formula. Well, in this case, what's playing the role of theta? So if I look here at my formula, what's playing the role of theta is exactly 2x. So if I plug 2x in here and I plug it in here, then I'll have a relevant formula for this. Okay, so yeah, if if theta is 2x, that's going to give us 1 plus the cosine of 4x over 2, because this doubles the input, doesn't it? Dx. Okay, at this point, I've got some options. I could split this up into 2 terms, right? I could use this whole idea that if c is non-zero, then this is exactly this. It's sort of common denominators in reverse. Instead of putting 2 fractions together, you're sort of ripping them apart. Sounds kind of brutal. Okay. Another thing we could do is actually factor out the 1/2. That's what I'm going to do. So let's factor out the 1/2, and we have to do it from each term here, each part. I'm going to write it like here, so it's really sort of suggestive of what I'm doing. Now, if I want to factor out a 1/2, you just have to ask yourself the following, right? So 1/2 of blank equals 1. Well, 1/2 of 2 equals 1. Okay. 1/2 of blank equals 2. I need a 4 here. And our factoring of the 1/2 takes care of this. Okay, so we have a couple like terms we can combine, but we don't have any more even powers. That's a good thing, right? So no more even powers. So once I combine these, we can just go ahead and integrate this carefully. So 2 plus 1, of course, is 3, plus 4 cosine of 2x plus cosine of 4x dx. I just want to recall something on the side. Okay, so assume, of course, m is not 0. So the antiderivative of cosine of mx dx, I call this the anti-chain rule. So it's the antiderivative of cosine, which is sine, same input, same argument, times 1 over the coefficient of x. You can convince yourself that makes sense, because if I take the derivative of this carefully using the chain rule, notice that's going to kick out a copy of m. This fraction has to be there to cancel with that m so that I get this integrand back. Okay, so if we're careful with this, that's going to help quite a bit here. So the antiderivative of 3 in respect to x, of course, is 3 times x, or 3x. Now here, you're going to see me use this. So that's 4 times. So I've got antiderivative of cosine, same argument, same input. But I need to multiply by 1 over the coefficient of x. So that's 1/2. Okay, so same thing here, same idea. Antiderivative, same input or argument, but I need to multiply by 1 over the coefficient of x. Plus c. Let's tidy this up a little bit. Okay, so 4 times 1/2, of course, is 2. So that's 2 sine of 2x plus 1/4 sine of 4x plus c. You could leave it like this. I don't have a problem with that personally. I think maybe it's up to your instructor. And if your instructor prefers, you can distribute the 1/8. Some do. That's fine as well. So 2/8 is 1/4. So 1/8 times 1/4 is 1 over 32. And so we get the following. So a little bit of a journey on that one, but we arrived safely home. And so now let's look at some integrals involving tangent and secant. Okay, so here we've got the integral of tangent to the 4th of pi x times secant to the 6th of pi x dx. One thing I found helpful when we've got an integral that involves tangent and secants is the following. write down what you know about tangent and secant in terms of the Pythagorean identity as well as the derivatives. What I find is if students get stuck, that gives you inspiration to try something. So this is sort of my recall. So there's the Pythagorean identity that might be helpful. And then let's also just write the derivative of, how about tangent? We know the derivative of tangent. That's exactly secant squared of x. And then the derivative of secant, remember that's the product of secant and tangent, both of the same angle x. So recall. And I do the same thing. So if I have integrals involving tangent or secant, I always write this down just because I know them by heart, but there's just something about seeing them visually that helps when one gets stuck. There's also similar statements for integrals involving cotangent and cosecant. I always write down the similar statements on the side as well. So let's sort of reason out what to do here. So I think about it as I've got two choices for possible openings, right? So one thing I could do is take a copy of secant squared from here and slide it to the side, sort of hoping to set up for a u sub. The other thing I could do is take one copy of secant and one copy of tangent and slide it over to the side. That would give me inspiration for a u sub. But in this case, only one of those makes sense. So do I want to slide over a secant squared or do I want to slide over a secant tan? You want to pick whichever one of those choices leaves all the rest of the powers even. Why is that the case? Because you're going to want to use the Pythagorean identity. So if I take out a secant squared and slide it to the right, do you notice what I'm left with? I've got a tangent to the fourth and a secant to the fourth, both even powers. That means this would be useful. If I try this instead, if I slide a copy of secant and a copy of tan over, I'd be left with a tangent cubed and a secant to the fifth. Those odd powers would not be so good here. This is my clear winner. See if you can convince yourself that's helpful. So let's go ahead and rewrite this as tangent to the fourth of pi x times secant to the fourth of pi x times secant squared of pi x dx. So I chose this. I took a factor of secant squared out of this and just sort of slid it to the side. This should look close to du when I make a substitution. So I'm going to say close to du. What I mean by close is it could just be off by a constant multiple. So if my derivative, my du, involves a secant squared, then my original function, my u, should be in terms of tangent. That means this needs to be in terms of tangent. Well, we're in luck. This is already tangent stuff, right? So the question then becomes, well, how do I turn this into tangent stuff? It's exactly this. So that seems pretty helpful because I can think about this secant to the fourth as secant squared squared. So yeah, this is exactly secant squared of pi x quantity squared. So let's write that. That's secant squared of pi x squared. Now, don't forget your goal. We want all tangent stuff here, right? So this is the point of rewriting that was we want to turn this into tangent stuff in a legal way using our Pythagorean identity. All right, so by our Pythagorean identity, we've got the following. So secant squared of an angle is equal to tangent squared of that same angle plus 1. So this will get replaced by this, but instead of theta, I'm going to see pi x. So that's tangent squared of pi x plus 1 quantity squared. So this got replaced by this by using our Pythagorean identity here. Okay, so now we can see the point of all of that algebra. The point of that was to set us up for a substitution. So we're going to let u equal the tangent of pi x. We're going to carefully take the derivative using the chain rule. So that's going to give me secant squared of pi x times the derivative of the inside, which would be pi, and of course dx. Don't forget your dx. We're hoping to replace this. So we just divide by pi. All right, so now we can replace this. That's exactly equal to this. So goodbye secant squared of pi x dx. You're getting replaced with 1 over pi du. And then this, so take a look here, this should be u to the 4th. And this should be u squared plus 1 quantity squared. Okay, so again, for following order of operations, we want to do this squaring the exponent first and then the multiplication. So let's see what we have. We've got 1 over pi, antiderivative of u to the 4th. And then again, we're going to use our favorite, a plus b quantity squared. So that's going to be u to the 4th plus 2u squared plus 1 du. Okay, so now be careful, distribute. Remember to add exponents when you multiply the same base. So this is u to the 8th plus 2u to the 6th plus u to the 4th du. Okay, so now by the power rule, this is going to give us u to the 9th over 9 plus 2u to the 7th over 7 plus u to the 5th over 5 plus c. Now we have to remember our substitution statement. So let's go back, look right here. And we can use this to go express our answer in terms of x instead of u. So yeah, everywhere I see a u, namely here, here, and here, I'm going to replace it with this quantity here, tangent of pi x. So that gives me the following. So I could write it as, parenthesis tangent of pi x to the 9th, or I could write it as tangent to the 9th of pi x. That's understood to be the same. Over 9 plus 2 tangent to the 7th of pi x over 7 plus tangent to the 5th of pi x over 5 plus c. And so just note let's see here. Why not? So say tangent to the m of pi x is the same thing as tangent of pi x quantity to the m. So that's what we mean by this, of course, with trig. All right, so let's try one more integral involving tangent and secant. Let's try tangent to the, I don't know, how about tangent to the third of theta, secant to the fifth theta, d theta, maybe something like this. Now, I mentioned before, it's a good idea to write down the Pythagorean identity and then just quickly the derivative of tangent and secant. And we said if we have a product involving tangent and secant, then I might consider, so it's not something I always do, it's just something to consider. If I have a product involving tangent and secant here, I might consider either sliding over a secant squared from here or taking a copy of each, a factor of each out of here, and sliding it over. So which do I choose? So mentally just try each, right? So if I do this, do you notice that the other two factors will be odd? So if I slide over a copy of secant squared, that would leave me with a secant cubed times a tangent cubed. Well, that's not good because I want whatever I slide over, I want the rest of the stuff to have even powers so I can use this. Now this is good. So suppose I take a factor from each of these and slide it over. What I'm left with are two factors that have even powers. So I would have a tangent squared secant to the fourth. That's really helpful because I'll be able to use this. So this wins. So you choose whichever puts you in a position to use this on what remains. So let's see what I mean. So that's going to give me a tangent squared of theta, secant to the fourth of theta, but to make that legal, right, that's tangent of theta, secant of theta. That's the same thing as this, right? The order doesn't matter. Multiplication is commutative. D theta. And we know this should look very close to du. And again, notice that this was good because what's left over has purely even powers, which means we're allowed to use this. Okay, well, if my derivative involves this product, then my original function should involve nothing but secants. So we need all secant here, secant stuff. So that's already in terms of secant, so I'm happy. I need to write this in terms of secants. Well, if I solve for this algebraically, I'll have tangent stuff in terms of secant stuff. So maybe we'll just note that. So if tangent squared of theta plus 1 is secant squared, I'll be able to replace this if I just solve this algebraically. So subtract 1 from both sides. And that's nice. I can write our tangent stuff in terms of secant stuff. Okay, so that gets replaced. I still have the secant to the fourth of theta and this tangent of theta, secant of theta, d theta. So I realize that probably looks like a mess to you right now, but after we do our substitution, it's going to be a lot simpler. So we've been setting ourselves up for a secant substitution for a while. Now we're just going to carry through with it. So we're going to let u equals secant of theta. And of course, du is equal to secant of theta tangent of theta. That's the same thing as tangent of theta times secant of theta. Okay, so let's see what we have here. So this is u squared minus 1. That's going to be u to the fourth. And this is exactly this. So let's call this du. So we've sort of, in a sense, tamed this, right? So by algebra, we can just distribute this. So let's go ahead and distribute this. So that's going to give us u to the 6 minus u to the fourth du. So that's going to give us, it looks like u to the 7th over 7 by the power rule minus u to the 5th over 5 by the power rule plus c. And then don't forget to back sub, right? We're going to plug this in for both of our u's. Okay, so when we do that, we get the following. So what are we left with? I could even drop these parentheses, couldn't I? So we're left with secant to the 7th of theta over 7 minus secant to the 5th of theta over 5 plus c. So that seems pretty nice.